All right. A very warm welcome to everyone here tonight. I'm Xavier, the chairperson of the Cambridge University Astronomical Society. We have a series of very interesting talks lined up for you this term, and to kickstart the series, Professor Roger Davies is with us here tonight to give a talk titled Black Holes, Galaxies, and the Nobel Prize. Before we begin, allow me to share a little bit more about our speaker. Professor Roger Davies is the first holder of Philip Wetton Chair in Astrophysics and a student of Christ Church College, University of Cambridge. His research interests centered on cosmology and how galaxies form and evolve. He has a long-standing interest in astronomical instruments and telescopes. Since 2014, he has been the founding director of the Oxford Hintze Centre for Astrophysical Surveys. Professor Roger Davies grew up in Scunthorpe in North Lincolnshire and attended John Leggett School. He read physics as an undergraduate at UCL and did a PhD at the Institute of Astronomy and Churchill College, Cambridge. Following that, he moved to the United States, working at the Kitt Peak National Observatory in Tucson, Arizona. Now part of NSF's NOAA lab. He became part of the 7 Samurai collaboration, which surveyed the distances and velocities of galaxies, discovering the Great Attractor. He moved to Oxford in 1988 to lead a team set out to build a UK 8 meters telescope that ultimately resulted in their membership of the Gemini Observatory. Since then, he has been project scientist for a number of instruments. He became head of astronomy at Durham University in 1994, returning to Oxford to Wetton Chair in 2002. He has pioneered the use of a new class of astronomical spectrograph to measure the masses and ages of galaxies, as well as search for black holes in their nuclei. He was head of the physics department at Oxford from 2005 to 10 and head of astrophysics from 2011 to 14. He is a fellow of UCL and holds an honorary degree from the University Claude Bernard in Lyon, France. He was president of the Royal Astronomical Society between 2010 to 2012 and has been president of the European Astronomical Society since 2017. He was elected to the Aura Board of Directors in 2021. Now, without further ado, Professor Roger Davies, please. Sorry, you are muted right now. Sorry, Professor, you are still muted.
Here we go. There we are. That's it. My apologies. Okay, thank you, Xavier. Now, so I'm guessing that you can see my slide as not quite full screen yet, but
yes.
Now it's full screen. Is that correct?
Yeah, that's great.
Good, and that's very good. Good, excellent. So thank you for that introduction, and just a few words of introduction myself. Here we go. So I'm actually in Oxford, as you probably realize. I'm at Christ Church in Oxford, but I was in Cambridge for a long time. I did my graduate work at the Institute of Astronomy, and I was a junior research fellow at Christ Church, which somehow slipped out of that web introduction that I provided. And I noticed, actually, I am a member of QS, and in a recent clear out, I did discover my card, which I realized sitting here I could have shown you, my life membership card. And I noticed Jonathan Shanklin is on the line, and I certainly remember that he was also, I think he was the president of QS at the time. Okay, so tonight is Burns night, and that's why I have as my background the wonderful mountain on the Assynt Peninsula in the northwest of Scotland, known as Sullivan. And I would strongly recommend that at your first opportunity, if you haven't done so, you climb it. So anyway, happy Burns night. And for those of you who have a glass of whiskey in front of you now, I will be joining you at the end of the talk. Okay, so I'm going to talk about galaxies and black holes and about how the Nobel Prize was won. And here's an outline, and the outline I realize is slightly misleading. So I'm going to have a very short bit on black holes from stellar death. Most of the talk is going to be about black holes in galaxies, with some focus on the M87 result and the Milky Way result. And the bulk of this talk will kind of assume that everybody knows it's straightforward and to measure the masses of black holes in galaxies. Of course, it isn't. So the last part of the talk, I'll just spend a few moments talking about how technology enabled this kind of work. So maybe in summary for that part up front, I should say that when I was in Cambridge, the measurements that resulted in the Nobel Prize were impossible for two reasons. So, you know, an interesting development over my career. Okay, so look, let's start about general relativity and black holes. So in very strong gravitational fields, we use general relativity to describe the motions of objects. And one of the predictions of general relativity is this idea of gravitational redshift. So as electromagnetic radiation tries to escape from the vicinity of a black hole, it is stretched and its wavelength is lengthened. And of course, this leads to the idea that there is a size beyond which the wavelength can't be lengthened anymore, the event horizon, from which no radiation at all can escape. And in a rather beautiful result, the whole complexity of GR is reduced to this formula in the bottom right-hand corner of this slide, that the event horizon, known as the Schwarzschild radius, is just given by twice Newton gravitational constant times the mass of the black hole divided by c squared. And for the sun, this is about 3 kilometers. So the problem here, however, let's move on to the next slide. The problem here was that in the early years of general relativity, the idea of a singularity, a point mass, was very uncomfortable, and people were not wondered, how can we ever really in real physical universe reach this theoretically hypothesized ideal situation. And one of the key pieces of work that was done just before World War II by J. Robert Oppenheimer and Hartland Snyder was this paper in 1939 about spherical collapse. And they did a calculation assuming perfect spherical symmetry and showed that they could that collapsing under spherically symmetric conditions would lead to an event horizon and a singularity. But the sort of view that this might be achieved in nature was thought to be very, very unlikely, because the strict spherical symmetry is just not going to happen anywhere. Of course, it's an interesting note that J. Robert Oppenheimer went on a few years later to lead the Manhattan Project and was the father of the fission bomb. So we move on 26 years to the mid-60s, and the 60s are a key decade for this story of black holes and galaxies. And in 1965, Roger Penrose brought a completely different approach to looking at the problem of gravitational collapse. And he used the methods of topology theory and was able not to use the spherically symmetric assumption, but use the concept of trapped surfaces to show that there's a point of no return beyond which the collapse to a black hole is completely inevitable. And you know, it's rather chastening to think that Roger did this piece of work in 1965 and he was awarded the Nobel Prize for it in 2020. So you know, it takes a long time for theoretical calculations sometimes to be verified by practical measurements, and this is one of the things that the Nobel Committee looks for. Okay, so a very quick section on stellar mass black holes, because this really isn't going to be much part of the talk, but you know, there are whole stacks, gigabytes on the internet about stars and stellar evolution. But the key point that I want to make here is that stars are actually very simple systems. They're just machines in which gravity and pressure are balanced. And in stars like our sun that are burning hydrogen to helium, they're in equilibrium, they're very long lived, and everything is in equilibrium for a long time. More massive stars live their lives more rapidly, and when they collapse at the end of their nucleosynthesis burning, that they will become white dwarfs, and there the pressure is the degenerate electron pressure from the Pauli exclusion principle that holds them up against gravity. Yet more massive stars cannot get enough support from that source, and they collapse to neutron stars, which we know as pulsars. You can see the Crab Nebula in the bottom right of this slide. In the top right is a planetary nebula with a white dwarf in the center of it. And neutron stars are held up by a similar degenerate pressure, but just at a much higher level. The densities of neutron stars can be up to about 10 to the 17th kilograms per cubic meter. And here it shows, as it says, black holes distort space-time. If you have an even more massive collapse, there is no source of pressure beyond that, and that's how you get collapse to a black hole. Okay, so this story starts really in the 1960s for stellar astrophysics with the first X-ray satellites that were somewhat surprised to detect highly variable X-ray emission. And these stars were soon, the X-ray sources were soon identified to be binary stars. And this, of course, meant that we had a good shout of measuring their masses. And in some cases, the masses were so large that they couldn't be neutron stars and were most likely to be black holes. Now, this is a complex story. The inclination is very difficult to determine in most cases, and the masses have uncertainties associated with them. It took a long time actually for the analysis really to tie down rigorously that some of these objects could be binary stars where the star is orbiting around a black hole rather than a neutron star. Okay, so look, just a quick primer on how we measure masses. So this is how we measure masses of anything in astronomy. So the sun, a galaxy, or a black hole. So let's think about the Earth going around the sun. The sun has a mass m. Here is the Earth in its elliptical orbit, which we're going to ignore for now. And what we're going to do is equate the gravitational force between the two objects, so gmm over r squared, to the centripetal force of circular motion. And then we're going to rearrange that equation, and we're going to end up with something that allows us to measure the mass of the object that's been orbited around. The mass of the Earth, or the tracer mass, cancels out in this little equality. And what you need to measure in order to get the mass is a velocity at a radius, and this is just the universal gravitational constant. And so if you can measure a velocity at a radius, you can measure the mass of the thing you're orbiting around, and of course that's how we know the mass of the sun. And of course, I just want to show you this diagram. I shall show you it again a bit later in the talk. But this is what the radial velocity of objects looks like as a function of radius if all the mass in the system is concentrated in the center, as it is in the solar system. And so you can see that the velocity that you measure, the orbital velocity, goes down as 1 over the square root of radius. Because, of course, in any given system, m in the center is constant. So you're just looking, if you want to find a system where you've got a black hole or a bare object or an object that dominates the potential, then you're looking for the signature of the velocity of the tracer that you're using falling like 1 over the square root of the distance between a radius. Okay, so now let's think about black holes in galaxies. And this is also a story that starts in the 1960s with the characterization of radio galaxies. So here is a relatively modern slide showing the radio galaxy in Virgo A, or the Virgo A radio galaxy, which is hosted by the central galaxy in the Virgo cluster, about 20 megaparsecs away, known as M87. And you can see this slide shows you from the lower left, which is a very long baseline interferometry measurement showing you the radio emission. on a sub-parsec scale. You can see in the next frame up that axis of that jet that you see is preserved when you go 500 times bigger to 400 parsecs, and it's preserved again out to almost a kiloparsec or so on the even larger scale. If you go on a very much longer scale on the right-hand side, larger scale on the right-hand side, that axis is sort of lost, but you see a huge amount of radio emission from which obviously has something to do with what's happening in the center of Virgo A. And although these things are, these objects today are not particularly common in the local universe, radio telescopes operating in the 1960s, the first aperture synthesis telescopes, were able to find lots of objects like this, but most of them were at great distances. And so you can see a typical structure is that you have a jet and then some extended emission at the end. Here you've got a jet, here a jet, similarly. So the most energetic of these objects were discovered by Martin Schmidt in 1963, the quasars, quasi-stellar objects. So these were radio objects which looked stellar when you found the equivalent object on an optical picture. And the quasars are enormously energetic. I mean, the radio galaxies are also very energetic, but the quasars are the most energetic, and they can emit about 10 to the 40 watts. So here's a competition. I have tried over several occurrences of giving this talk to find an appropriate way of trying to get across what 10 to the 40 watts are, but unfortunately nuclear power stations and so on don't help very much. There are still a large number of zeros after the number of nuclear power stations. So a good simile, excuse me, for what 10 to the 40 watts is would be helpful. Okay, so the question arises then, since these objects were observed, at least in their centers, to be variable, the puzzle is, how do you get such large amounts of energy out of the small volumes that are implied by their variability? And there's a beautiful paper by Donald Lyndon Bell, who is shown here next to Martin Schmidt. So Martin Schmidt's the one in the bow tie, Donald is the one with the less hair. Martin discovered the quasars, and in 1969, Donald Lyndon Bell wrote a paper in Nature trying to understand what was going on in the nuclei of galaxies. And he proposed that the only viable source of energy for the radio galaxies was material falling onto a supermassive black hole. In other words, the transformation of gravitational energy into electromagnetic energy. And for this, Schmidt and Lyndon were awarded the Kavli Prize in 2008. Now, it's actually quite a tricky thing to measure the mass of black holes in galaxies or radio galaxies, and it took a big effort by Hubble Space Telescope teams and teams working from the ground. I'll come to how they did that towards the end of the talk, to measure the masses of black holes in galaxies, but I'll sort of skip over that for the moment and bring in and just explain slightly about why that is so difficult. So in Lyndon Bell's paper, he uses the total amount of energy which must have been generated to make the big radio sources. He postulates what would be required in terms of gravitational energy and what mass, therefore, you need to look for to make this work. And he comes up with, it's an order of magnitude calculation that he's presenting, but he comes up with masses between 10 million and 1,000 million solar masses to make this trick work. And so you can work out essentially what the sphere of influence of such an object is out to in galaxies where you might expect to find these things. And typically, and the little equation is given here, but it's essentially directly from the virial theorem. So it's not a complicated calculation. You can work it out another way, which I'll come to in a moment. you can say, for example, that the black hole dominates the potential within a radius before the star mass is equal to the black hole mass as you go out with radius, right? So you might say the black hole's dominated as long as it's got twice as much mass as the mass of stars out to a certain radius or something like that. And when you do those kinds of calculations, you find that the black hole potential only dominates over the stars out to a few tens of parsecs in the most massive nearby galaxies. And if you convert that into what you'd expect to see on the sky, it turns out to be a few tenths of an arc second. Now, for those of you who have looked through the QS telescopes on Madden Rise, you will be aware that the size of the images that you see in those telescopes at the very best is a few arc seconds from that location. If you go to the very, very best sites in the world and you take the very rarest but best conditions, you might be fortunate to be able to record images that are as small as half a second of arc. Getting a tenth of a second of arc has not been possible, was not possible certainly in the 1960s, and it only became possible in the 1990s. So this was a very, very difficult thing to do, and the reason it became possible in the 1990s was twofold. One was the launch of the Hubble Space Telescope, taking it above the atmosphere, and the other was the development of a technology known as adaptive optics, which I'll come to a bit later. Okay, so following on about what powers radio galaxies. So these measurements were made over the 3 decades, really, since 1990. And the motions of the gas and stars were measured, and the presence of black holes in the range of 1 million to 10 billion times the mass of the sun were implied to be deep in the center of bright luminous galaxies. And the way the radio galaxy is thought to produce its radio emission is through accretion of material onto that nuclear region. And of course, because it has non-zero angular momentum, it forms a disk around the black hole, and most of the electromagnetic radiation is produced in the disk, and jets are produced out of the poles of the disk. I'm not going to say very much more about this, other than the key component is having a very massive black hole at the center. Okay, so decades pass, and we are able to measure the masses of a few dozen black holes, galaxies in the center, black holes in the center of a few dozen galaxies, excuse me. And we can make a plot of the mass of the black hole against the mass of a galaxy. And what we find is that there is a linear relationship such that the mass of the black hole in a galaxy is typically 1/500th of the mass of the galaxy. Okay, now this is a very puzzling result. And this is why it's puzzling. Here's the problem. So the black hole has a mass of about 1/500th of the galaxy mass. So now if you do this calculation about where does the black hole potential dominate, how far out in the galaxy does the black hole potential dominate, the answer is that it's dominant over about 1/100000th of the volume of the galaxy. So how is it possible that the mass of the black hole is directly proportional to the mass of the whole galaxy, which of course extends over tens of kiloparsecs? So this is a bit of a conundrum. Why is this the case? And this is where we have to think about our ideas about how galaxies form. Sorry, excuse me a moment. Just need to keep my eye on the time here. So good. Okay, so let's go forward. Okay, so galaxies assemble out of the large-scale structure, and what I'm going to show you here is a cosmological simulation of what happens just to dark matter. So this is actually a very early cosmological simulation. And so let me just show it to you. And oh, this is early because it only has dark matter. So it starts off just after the Big Bang, and the material in the universe is very uniformly distributed. And when we start the simulation, what happens is the dark matter, where there's a little clump of dark matter, there's a little bit more gravitational attraction that brings in the dark matter from around it. It's got yet more mass, and so that attracts more dark matter. And so there's positive feedback, and the areas which started off with a seed of a little extra mass have grown into things that will become clusters of galaxies. And here's now a picture of what we now call the cosmic web. I'll run that again. And so there's a positive feedback where dark matter halos form, and in those dark matter halos, galaxies form and clusters of galaxies form. So the dark matter halos merge together, making ever more massive galaxies, ever more massive halos containing ever more massive galaxies. Right, so let's, okay, so what's happening here is a very complex physical process, which is proves very difficult to try and understand in detail. So this brown central circle is the dark matter halo, and of course it will have some spin, and it will have gas cooling and falling into the center, and that cool gas, the cold gas, will form stars. Those stars will evolve, and the most massive stars will explode as supernovae and enrich the interstellar medium with heavy elements. And every now and again, as we saw in the simulation, another galaxy halo will merge with this halo. And so there's a lot of complex astrophysics going on as we make individual galaxies. So one of the things that happens, as I said, is that, and I showed in the simulation, is that galaxies collide with each other and they coalesce. And this is a simulation that I'm taking from YouTube, so I'll play it. It's a simulation of what's going to happen to M31 and the Milky Way as time passes. And so remember, I'll play it now. So here we go. So here's our own Milky Way, a barred spiral galaxy look, and the shot will pull out, and in the bottom left-hand corner, the Andromeda Nebula will appear. And so when the Milky Way's edge on like that, look, Milky Way and M33 are not edge on, so these are not aligned, but they are both thin disks. Both galaxies have thin disks. So now you can see M31 edge on, and you can see what's happening over billions of years. They pass by each other. They're drawn together under the influence of gravity. And the first time they pass each other, they stay separate. And look what's happening to M33 here. But the second time they pass by each other, they can't escape each other's gravitational attraction, and they merge to form a single object. And if you look carefully at this simulation, you can see that there are shells and structures at large radii in the end product. The end product is not a thin disk galaxy, but what we call an early type galaxy, or an elliptical galaxy. So the end product is an early type galaxy. So when disk galaxies merge, they change the morphology of the galaxy and produce something which is has a completely different structure. Okay, so now we know there are black holes in the center of galaxies. What's their role in galaxy formation and evolution? So one of the things we can do, simulations, of course, cosmological simulations and detailed simulations of galaxy interactions allow us to do experiments with the universe that we would not be able to do in Obviously, we can't do it on the real universe. And so what I'm going to show here are two simulations which are identical, except for the fact that in the left-hand one, the black holes have been removed from the centers of galaxies, whereas on the right-hand one, the black holes are there. And this is just an illustration of what's happening to the gas. But what you'll see is the large-scale structure traced out in the gas, and the red color will show you the gas temperature. So let's run this. I'll run this a couple of times. So here you can see the large-scale structure forming, and immediately on the right you see that the gas heats up more quickly. It's much more extensive, and so the black holes generate a lot more hot gas, and that gas is much more extensive. So on the left-hand side, you see that it really only extends to the galaxies in the very densest parts of the simulation. So it's clear that the presence of black holes in galaxies has a rather fundamental impact on the time evolution of the galaxy. So this is where we get to the point where we first resolve the conundrum of why the black hole mass is in proportion to the galaxy mass. So what you see happening here is that the galaxies grow through mergers, and as they grow through mergers, the black holes that they have in their centers also coalesce. And so as you start from small galaxies and they coalesce to bigger galaxies, small galaxies to small black holes in the center, you naturally build a connection between the mass of the galaxy and the mass of the black hole. And so we call this the co-evolution of galaxies and black holes. But the effect of black holes on galaxy evolution is much more dramatic than that, because as I showed you, they generate an enormous amount of hot gas. They dump a lot of energy into the interstellar medium, and so the radiation from the accretion disk and the jet that you get from the active episode of galaxy evolution, that heats the cold gas, which normally would be just forming stars in a galaxy, and it suppresses and ultimately stops star formation. And this is actually the mechanism that we believe stops star formation in the most massive galaxies. And as I said, it naturally links the mass and the size of the stellar component of galaxies to the black hole mass. And so this is this concept of the assembly of galaxies through mergers is what links their black holes and their larger scale, their global properties. Okay, now, so this is a story which, that story kind of was established maybe 10 years ago, but what's happening now, it got very hard to do many more galaxies, to measure the black hole masses in many more galaxies. And this story now is moving into an epoch where black hole masses can be measured in different ways. And I'm going to cover 3 of them. There are 1 or 2 more, but I'm not going to cover all of them. So one possibility is to change horses and go to much longer wavelengths. So the ALMA, the Atacama Large Millimeter Submillimeter Array, high on the plateau in South America and Chile, that can, because it's working at millimeter wavelengths, and because it has very long baselines and large number of telescopes, it can detect emission from carbon monoxide close to the nuclei of many of these galaxies, and it can measure the velocities of that gas within the sphere of influence. And this is proving to be a very rich source of black hole measurements. And I'll just show you one recent highlight from this kind of work done here by my colleague Martin Bureau in the WISDOM collaboration, which is a collaboration which also with Cardiff. So here's a galaxy NGC 383, and on the left hand side here you see the large scale radio structure, from the VLA. So you see the jet in the middle and the sort of large scale extended emission at larger radii. If you then go to much higher radio resolution, you can see this nuclear emission and the jet. And the HST picture shows this beautiful spiral structure right in the core of this radio galaxy. And the right-hand frame is hypothesizing what it might look like on even smaller scales. That is not an image of the center of this galaxy. That's an image of a circumstellar disk, which has been taken by ALMA. But you can predict on the basis of these images, which show you what's the distribution of stellar light, you can predict what you would expect to see from the velocities as a function of radius that you would measure in the CO gas. And that's what's on the lower frame here. So this is so-called a position velocity diagram. So it shows the velocity on the y-axis and the position with respect to the nucleus on the x-axis. And so what this is a prediction of what you'd expect if you took a line along here and you measured the velocity at each point along this line. So at one side of the galaxy, you'd find a positive velocity, the gas is moving away from us, and on the other side of the nucleus, you'd find a negative velocity, the gas is relative to the center coming towards us. And because you have an image of the galaxy, you can work out the likely amount of mass at each point, and so you can work out what you would predict for the velocity as a function of radius in the case of there only being starlight, and in the case of there being a black hole of the mass that you might expect. And so you can see here, that's what's done here. So the prediction for no black hole is a much shallower slope, whereas the prediction with a black hole is this funny shape here, same here. And of course, this part, the part that goes, the part that goes up here, that is the Keplerian part of the shape. And so this is in fact what you see in NGC 383. So this is the same three predictions here superimposed on the data. And so you can see that here's the data. Just look at this before we look at the predictions. So you can see that the velocity stays constant around 200 kilometers a second. There's then a little bit of rising here, a very steep fall to something again that goes up, well, it goes down here, but it's an increased velocity before it settles down to the value you'd expect just from the stars. So you can see here the blue contours show you what you would expect on the basis of the starlight alone. On the right-hand side, you see what you'd expect on the basis of the black hole alone. And the reason this isn't a pure Keplerian, going to very high values is, of course, it's all been convolved with the beam of the telescope and so on. But you can see that the middle frame showing the prediction of the black hole plus stars is the thing that really does fit the data properly. And the fit that this gives is a black hole mass of 4 billion times the mass of the sun, and a mass to light ratio in the H band for the stars of 2.8. And you can see here that the error bars on this are getting pretty small. So these are actually very precise measurements. So that's something to look out for. There'll be a lot more of these coming along. Now, this is a result that got a great deal of publicity and that you will have undoubtedly seen. And it isn't going to be possible for a large number of objects, but it's such a wonderful result that it's worth covering in this topic. So I spent a lot of time talking about M87. I showed you the beautiful radio data. This is an optical picture of the central galaxy in the Virgo cluster, M87, and it's this is a large scale here. This is 200 parsecs across the galaxy. Half the mass of this galaxy is inside a radius of about 30 kiloparsecs. So it's a huge monster galaxy. Now, the way what was done here is that an international collaboration to use an array of radio telescopes across the globe was put together in order to record the radio signals from each dish along with a very precise atomic clock. And then all this data is then shipped to a central station, and an image in the what we call the UV plane, the image of the motion of that shows the motion of the telescopes when looked at from out in space, the radio signal that you see along each of those blue paths, and you then do a complex analysis because there are a lot of potential outcomes to finding an image from this data, but the best image, the optimum image, is the one that's very famous, this one. But this is a shadow of the black hole here. This here is the shadow of the black hole in M87. Just to go back here, you can see the telescopes are here right across continents. So there's 2 telescopes in Hawaii, there are 2 telescopes in Chile, a telescope at the South Pole, one in Spain, one in Arizona, and one in Mexico. So this is very large baseline interferometry done at really rather short wavelengths, 1.3 millimeters. So this was a real technical tour de force to produce this image. Now, so here we are. This is we've got a picture of the black hole in M87. We've got the optical picture, we've got the radio jet, and right in the very core, we have the reconstructed image from the 1.3 millimeter data from the Event Horizon Telescope. And the diameter of this ring, D, tells us, sorry, excuse me, not D. The diameter of this ring, which is 3.8 micro arc seconds. Okay, so not arc seconds, not milliarc seconds, but millions of an arc second. So very, very small, 3.8 micro arc seconds. That diameter is just, if you work out the theory of all this, it's just the gravitational constant times the mass of the black hole divided by the product of the distance to the object times the speed of light squared. And so, of course, we know the distance and we know everything else, and we now know the size. And so that gives us an estimate for the mass of the black hole in M87 of 6.5 billion solar masses. And just to give you a scale here, the ring, the size of the ring is about 700 AU across, and that's about 5 times the size of the orbit of Eris. So this is a really small scale in the nucleus of M87, which is of course why we have the sensitivity to do this. Okay, so before we leave M87 and go on to the Milky Way, you might have thought it will be somewhat easier to do the black hole in the center of the Milky Way rather than in the center of M87. And so perhaps I'll leave that question for you, and maybe we'll come to that at the end. Let's just check the time here. Okay, so a black hole in the center of the Milky Way. So here's the center of the Milky Way. This is a very, very wide field image. You can see the size of the full moon in the top right. The galactic center is indicated by the yellow star. It's 25,000 light years away, 8 kiloparsecs away. Now, after a huge technical effort, it's been possible since the 1990s to monitor the positions of the stars that are orbiting around the center of the Milky Way. And this animation shows you this. And so let's just run it. So here we have the motions of the stars. We're already in 2004, 2005 now, and you watch, it's the yellow orbit that's the key orbit running around until recent times. Let's run that again. Sorry, let's go back. Here we go. So you can see it gets very near. Actually, this is not, sorry, I beg your pardon, this is not the version of that thing that I wanted to show you. There is a more recent version, which I thought I'd picked up, but obviously I haven't done, which shows that yellow orbit, the star, which is called S2, come round in recent times, 2018, very close again to Sagittarius A, the center of the Milky Way. So we know that orbit very accurately, and we can use it to work out the mass of the black hole in the Milky Way, 4 million times the mass of the sun. Okay, so having done that magic trick, how does this tell us that this is a black hole? It says there's 4 million solar masses in a rather small volume, but it's not enough to be absolutely certain. It's nothing like the event horizon. It's much bigger than that. So we have to get some indication of how big that volume might be, and the way we do that is by monitoring the variability of the X-ray and infrared sources in the center of the Milky Way. And you can see here, right in the middle of this frame, the X-ray emission from the center of the Milky Way getting brighter and fainter. And that X-ray emission flares on timescales of about 40 minutes. So it goes up by a factor of 4 in brightness in about 40 minutes. And so what that tells us is that if we have a small but extended source of emission in the center of the Milky Way, then on the side of that emission that's nearest to us, the radiation from that near side of the source arrives to us first. And so if it's getting brighter, we see if it gets brighter instantaneously, we see first of all the radiation from the near side, and only the light travel time later do we see the radiation from the far side. And so an estimate of an estimate of the light travel time across this source is just the time it takes for the source to brighten in light years, or light minutes in this case. And so this tells us that the size of the emitting region is roughly 40 light minutes. That's 5 times the distance from the Earth to the Sun, or the radius of the orbit of Jupiter. So now we can hypothesize that we've got 4 million solar masses of mass inside a solar system scale volume. And so this is getting to be much more compelling that we can have a black hole. It's not that there are no other explanations, but they're not stable, for example, and they're not compelling at all. So having made these measurements, Reinhard Genzel with his group working in Chile, and Andrea Goetz with her group working on the Keck telescope in Hawaii, were jointly awarded with Roger Penrose the 2020 Nobel Prize for the prediction that black holes are a robust prediction of general relativity, and to Genzel and Goetz for the empirical observational work. Okay, so why did it take so long from 1965 to the midway through this decade to get this result? Okay, so I'm going to give you a complicated answer, but the simple answer is the technology that was used to make these measurements was not available in 1965. In fact, it wasn't available in 1985. It became available once the technology that had been developed as part of for defense in the Cold War was declassified at the end of the Cold War in around 1990. And the first thing that happened that enabled us to make these measurements was the development of a technology known as adaptive optics. So here, just to give a scale of the problem, I've said it's the center of the Milky Way is 25,000 light years away. The orbit of S2 is a couple of light days across. That's 1/10 of an arc second on the sky. It's very small, far too small to have been observed even with the 8 and 10 meter telescopes that were available to us in the very early 1990s. It's 20,000 times smaller than the full moon. So we needed to use some kind of image sharpening technologies. And there were image sharpening technologies available. They were just not very effective. And so the image sharpening technologies that we have developed have involved the use of deformable mirrors, very fast deformable mirrors, high-speed real-time computing, and correcting the deformed wavefront that enters the telescope for the deformations that are introduced as the wavefront passes through the Earth's atmosphere. So the irony here is that the light from celestial objects travels, astronomical distances to reach the top of the Earth's atmosphere, and when it reaches the top of the Earth's atmosphere, the wavefront is precisely planar. So if you were, that's why Hubble Space Telescope can take such sharp images. But once it impinges on the Earth's atmosphere, the inhomogeneity in density in the cells, which are typically 10-20 centimeters across in the Earth's atmosphere, cause the wavefront to become distorted, and the rays of light are just very slightly bent, which is why you see, when you look through a small telescope, you see an image moving around, and so it is in a small telescope. In a large telescope, you just see a blurred image. And so I'm going to show you an animation for how this works, and it's quite a long animation, so I think I can talk while it continues to run. So this animation is provided by the Gemini Observatory, and it shows their adaptive optics system. So let's just run it. So here we are at the Gemini telescope on Mauna Kea, and this is their laser guide star adaptive optics system. Now, the big problem here is that if you're going to correct the incoming wavefront from the universe, you need to have a wavefront whose deformation to act as a beacon, to act as a standard. And if you have a bright star, then that can do the job, and you can do adaptive optics correction, sharpening images around a bright star. But of course, for most things, and that works very well, for example, for exoplanets and stuff like that, where you do have a bright star. But most objects that you want to look at, in particular the nuclei of galaxies, don't have bright stars in handy places, and so you need to generate your own, and that's what all this stuff about a laser guide star is. So this is showing the sodium laser being shot up into the Earth's atmosphere from the Gemini telescope. When it reaches an altitude of 90 kilometers, it hits a band of sodium atoms, actually, which originated meteorites. Those sodium atoms glow resonantly in the yellow light of sodium D, and that provides a return signal back to the telescope, which has passed through the Earth's atmosphere in a way that you can then work out. So the light hits the primary, goes to the secondary, and then comes through the hole in the secondary mirror to the Cassegrain focus around the business end of the telescope, and is injected into the adaptive optics instrument. So here we go. This is the adaptive optics system. And what you'll see here is a mirror that directs the light into this system on the right-hand side here, which will become transparent. There we go. Here's the light coming in. It's directed to the right here through an optical system. And it's split by a dichroic into red and blue, but without any high-tech correction. There we go. There's the signal. That's what the image looks like on the screen, right? So now what we're going to do is to use the blue light, which passes through the mirror, and we're going to analyze that light using a wavefront sensor, which is, and we're going to work out how deformed these wavefronts are. We're going to close a feedback loop, and we're going to drive a deformable mirror with the complementary shape to the incoming wave fronts, and we're going to make them plane wavefronts again, so we recover the diffraction limit of the telescope, not the degraded images from that have passed through the atmosphere. And there you can see a beautifully diffraction limited image. Okay, so I remember in 1990 or 1991, I went to the Kirtland Air Force Base to look at their laser guide star adaptive optics system with Bob Fugate, who was one of the chief architects of these systems in the military. Of course, they were used primarily to image satellites looking upwards. So this was a technology that was declassified. The declassified technology itself wasn't good enough to do the job we wanted to do, but it was it was an excellent start. Okay, the second thing. So that's the first thing that was impossible in the 1960s or in the 1970s when I did my thesis. You couldn't you couldn't sharpen images and remove the blurring due to seeing. The second thing you couldn't do was to take a panoramic image in the infrared. There were only one element detectors in the infrared in the 1970s. And it again was, this happened a little earlier. Companies started to make small infrared detectors, a few dozen pixels on a side, and they were very revolutionary. It was only later that the large format, really sensitive infrared detectors became available. And of course, the reason you couldn't do this work in the 1960s, 1970s, and even in the early 1980s was that the Milky Way is shrouded by 10 to the 12, a factor of 10 to the 12 diminution in the radiation that reaches us. And so you couldn't see through the dust, basically. You couldn't see the center of the Milky Way at optical wavelengths. You needed infrared detectors, and infrared detectors, again, were a defense technology that was declassified at the end of the Cold War. And that's why in the 1990s, all this work took off. Okay, so what to take away from this talk? It's more or less an hour. Black holes exist in binary stars, at the center of the Milky Way, and at the center of other galaxies. And they range from millions to billions of solar masses. They power active galactic nuclei, which are much more common in the early universe, or let's say at a redshift of 2 than they are today. They produce huge amounts of energy. That energy drives the AGN, drives radio galaxies, drives quasars, and it quenches star formation in the most massive galaxies. Galaxies are built through mergers, and that's why we see the co-evolution of galaxies and black holes, and that's what produces the relationship between the mass of a galaxy and the mass of its central black hole. And then the final part of this talk just shows you how technology drives progress. Advances in technology drive progress in astrophysics. So I think with that, I shall stop talking and ask you if there are any questions.
Right, thank you, Professor Roger Davies, for the wonderful talk. We have about 15 minutes now for questions. So if anyone would like to ask a question, please raise your hand using the reactions button on the bottom of the toolbar on Zoom, and wait for you to be called. Or if you prefer, you can also type it in the chat so that we can read.
Oh, we've got 2 things in the chat. Okay, so should I just take the questions in the chat?
Yep, please feel free to do so.
Fine. Okay, so a question from Martin Bonner. Why do merging galaxies merge the black holes? Okay, so the galaxies, I guess you could look back at that simulation. You can see that as galaxies merge, the centers of the galaxies become a single center, right? So they so those 2 black holes do become close to each other. Now, it does take a long time, and this is actually a source of current research. It's not so easy to get them to coalesce, but given that we see that we have this relationship between the mass of the black hole and the mass of the galaxy, we're pretty sure that that's what happens. but it does take quite a long time, too long. The calculations suggest that it takes too long, the calculations we've currently done, than to really establish this relationship we've seen. So something is going on there in the complex astrophysics of the dust and gas and stars and dark matter in the cores of galaxies, which cause them to coalesce. Okay, so here's another one from Michael C. Will the James Webb telescope help further? Yes, absolutely. So James Webb, fantastic achievement. There's a couple of things I meant to mention in the introduction, and that was one of them. What an achievement by ESA and NASA to have it now at L2. Fantastic. Yes, it will. It's a 6.5 meter telescope as opposed to Hubble's 2.5 meter telescope. So it can do the same kind of work somewhat further away. Of course, it only works in the infrared, so that does slightly limit what it can do because that's a longer wavelength. And so the lambda over d, the diffraction limit, it is not that much better than Hubble, but it can see, it will be able to work at much greater distances. And so indeed, it will be able to look for black holes at large distances. I'd say that probably isn't one of its fortes, to be honest. It can do it, but probably there are other better ways to do it, some of which I've mentioned today. Let's moving down. So this is from Jonathan Shanklin. Hello, Jonathan. Does the fact that the Milky Way has a relatively small black hole and the fact that it still has spiral arms imply that it's only merged with much smaller galaxies? Now, this is a very intriguing question. Thank you, Jonathan. So it is a small black hole, right? But it's also a very small bulge. So one of the details that I didn't cover is that what the correlation really is between the mass of the black hole and the mass of what we call the spheroidal component of the galaxy. So the spheroidal component is the bulge, and so although the Milky Way is, for example, more or less the same mass as M31, M31, the Andromeda Nebula, has a much bigger bulge and a much bigger central black hole. And so, yes, I think that the mass of there's a very interesting line of research which is active here in Oxford by a research fellow called Becky Smethurst, as to how you might build black holes by secular processes in small bulge spiral galaxies. And in fact, she looks at galaxies that are even smaller. I mean, they don't have any bulge essentially, and tries to work out how they might generate modest-sized black holes, and has shown that this can be done. So I think probably our own spiral galaxy would have been very badly if it merged with a galaxy the size of M31. Essentially, it's destroyed, and that clearly hasn't happened. So yes, I think it probably had a seed black hole there from these secular processes that Becky is looking at, and then maybe smaller mergers with satellite galaxies have built it up a little bit. But it is very small, 4 million solar masses, as opposed to M31, which is at least 10 times bigger. I've forgotten the exact number. And what was wrong with the so this is Steve Hubbard. What was wrong with the 1939 proof? Well, it was simply that the assumption of spherical symmetry was felt not to be achievable in nature. I think that's really so. There's nothing wrong with it, as it were, but it wasn't thought to be a likely anything that's likely to have happened in nature. And then David Gwynn. Right, the supermassive black hole in Tonnan-Zintler 618 has a supposed mass of 66 billion solar masses. Can this be true? David, I think you've got the lead on me here. Do you mean TON 618 or do you mean NGC 618? Can I ask you that? You mean TON? Okay, I absolutely don't know, and I doubt very much that it can be 66 billion solar masses. That's a very high number. We do see galaxies that have much higher black hole masses then you would infer from their bulge mass. But we believe that in the cases, there's a handful of such cases, we believe that those galaxies have been stripped of much of their bulge mass in some kind of interaction. So the black hole is still there, but they've lost the bulge. So they appear to have, or lost much of the bulge. So they appear to have a much more massive black hole than they should have for that bulge size. But 66 billion solar masses is way off scale. So I'm not aware of that result, I have to say. What motivates you to pursue a career in astrophysics? Well, it's bloody exciting, isn't it? I mean, you know, what better way to spend your life than exploring the universe and getting paid to do it, and actually teaching other people and inspiring other people to follow and to make even further advances than you yourself have managed to make. So I mean, I'm towards the end of my career now. I'm not about to stop doing astrophysics, but I have to say, you know, I have given you a sense of some of the remarkable things that have happened that were totally impossible when I was a student, and I'm sure that will also be true of today's students. And so there's a great deal of excitement ahead. We've already mentioned James Webb Space Telescope. Now, what's the next one? Jim Slight. If since the beginning of time, primordial black holes have merged, has there been enough time to merge supermassive black holes? Okay, so this is a different kind of story, I think. So the answer is yes. I mean, supermassive black holes have merged. You know, the ones that are millions of solar masses might now be tens of millions of solar masses. We don't expect them to have had lots and lots of mergers. So this story is how you make massive galaxies. So that kind of came out when we talked about, you know, galaxies with small bulges. There are other things at work there. But for massive galaxies, yes, the supermassive black holes have merged. How are we doing?
We've got a couple more minutes, so if there are any other questions.
Okay. Thank you, David.
All right, if there are no other questions, that will be it for tonight. Thank you everyone for coming, and I hope you've enjoyed the talk. And thank you once again to Professor Roger Davies for such a wonderful talk. And yeah, good night, everyone.
Thank you very much. It was great. I'm terribly sorry I couldn't be in Cambridge with you. Enjoy the rest of Burns Night.